And this is why, for example, you cannot run your computer even faster, because then things will overheat if you run it too fast. So this is it wastes energy, and it limits the speed of things. So that's a big problem, and we should think about how to actually get rid of heat from information processing devices. Okay, so majorization, I will get back to more what it is, but it's a related notion to entropy, but it's different. It's a way of comparing which of two distributions is more random than the other. And it enters naturally if you consider randomizing dynamics. So it's actually, if you ask, oh, I have some probability distribution or a quantum state, and I zap it with some randomizing dynamics, then it normally turns out that the state afterwards is majorized. I think it's also more higher level now that it's fascinating that there seems to be a kind of meta-theory on top of physics, which is about how information flows between different systems. There seems to be a lot of phenomena, including life, that are not really about the substrate, that they are about the atoms and the chemistry, but about the mechanism, which seems to be more abstractly about data and data processing. If you want to make such a claim concrete, that there is a meta-theory of information flow, yada yada, I think it is natural to go into this language of elements to which you assign probabilities, and then entropy and information theory will enter into that naturally as well. And actually, if you really want to go full out and say, oh, it doesn't depend on the underlying theory, you shouldn't even assume quantum theory. Right? So you should go to generalized probabilistic theories, which is what we will do. So the general overview is, I know this is about quantum stuff, but I'm going to spend some time on classical entropy, because a lot of the quantum stuff actually comes from there. Then quantum entropy. Post-quantum entropy, meaning generalized probabilistic theories, and then the plan at least is stop. I get to here today, and then the second part would be classical majorization, quantum majorization, and then post-quantum majorization. When I wrote my abstract, I wasn't sure what this would be, and this was a while back, so I started thinking about it. And also Howard Barnum and John Barrett have a presentation on that. So I'm not trying to steal from their presentation, but I will say some thoughts about it. And I'm just trying to prepare you for their presentation, okay? On that. So part one, information entropy. So I didn't want to write classical, so it's information entropy. Here are two nice quotes. So Shannon says, if the number of messages in the set is finite, then this number, or any monotonic function of this number, can be regarded as a measure of the information produced. And then he says, oh, the most natural choice is the logarithmic function. So he seems to be fairly, what's the word, easygoing about how you should quantify this notion. She looks unhappy with that statement. Don't you think from this quote that he's? I think he's pointing out, oh, you could do it in many different ways. That's going to be my message. But then Jaynes when he's trying to justify his maximum entropy principle, he says, oh, the great advance of information theory is that we've seen that there's a unique, unambiguous criterion for the amount of uncertainty in a distribution, and this claim is just too strong. And that's one reason to be hesitant about this principle of maximizing entropy. So I'm going to argue that there are many different ways of quantifying entropy. Okay, so probabilities, it starts with probabilities. And someone told me the other day that probabilities are about Kolmogorov's axioms rather than necessarily operational relative frequencies or subjective probabilities, if I interpret this view correctly. Okay, so these are the Kolmogorov axioms. Fairly straightforward. We use them all the time in probability theory without thinking. There's some weight that you assign between 0 and 1. You have these different criteria, that we use them all the time. And the way I think when I do probabilities is I think of them as my subjective, the odds that I put on different things happening. Okay. So that means that if you say our probabilities are subjective, so more concretely, different people assign different probability distributions to the same events. It doesn't have to be, it's not about consciousness, it could be machines that do some processing. But now if I always like this example, if I flip a coin, okay, now I see what it is. I don't know whether this is called heads or tails, but I see. Yeah, so to me, this is 1, 0. Okay, like I know that the state, which state it is, but to you it's half-half.
Okay? No, to us it's clearly tails, because if it had been head, you would have known. You would have seen the wind's head.
You were right. I'm defeated. And but if there had been another type, if I hadn't given you that extra data, right? I gave you extra information so you could update your. If you hadn't heard what I said, or if you hadn't processed that, then you would have said half-half. Right? Okay, so that means the entropy also as an object is associated with both the observer and the object. Okay, so some simple examples of entropy measures. The most famous one is the Shannon entropy, or in the quantum case it's called the von Neumann entropy. Thermodynamics is Gibbs with a KB, a constant in front. Then there are the Renyi entropies, which is a family where you have a number alpha, normally, or it's greater than or equal to 0. Special cases of these Renyi entropies are if you put alpha as 0, then you get this. So that just means that if a probability is greater than 0, you put a 1 here, otherwise you put a 0. So this just counts, is the number of, oh, I put the sum outside, sorry. Take the log outside there. So it's the log of the number of non-zero probabilities. You can use L'Hopital's rule to see that if you take the limit as alpha goes to 1, it's not so helpful to plug it in straight away. Then you recover this guy. So it's, in that sense, it's a special case of this family. A common one to use is, here I put the sum in the right place, is S2, which can be called the collision entropy, because this is the collision probability, meaning if you have two samples from the same distribution, what is the probability that they will give you the same outcome? So probability of getting heads twice when you flip the coin is probability of heads times probability of heads. You have to also add probability of tails times probability of tails. Right? So this is the collision probability, and that's, the quantum purity is basically the quantum version of this collision probability. Then there's this infinity one, which if you think about it, you'll see that only the max probability survives. Did I miss a minus sign there? Sorry. This should be a minus sign here. So it's 1 over P max, or you put the minus sign here. So this guy is called the max entropy. This guy is the Shannon entropy, collision entropy. This one is normally called the min entropy. This is max because it's greater than or equal to any of the others, and this is min because it's less than or equal to any of the others. Okay, so which entropy is best? Which one wins? So the first, okay, all answers seem to be it depends, but the first one is it depends on your axioms. For example, you can place certain demands on how entropy changes when functions are applied to the sample space. I mentioned that one because it's an unusual axiomatization, which is by John Baez and Tobias Fritz and something Leinster.
Tom.
Sorry?
Tom.
Paul?
Tom Leinster.
Tom. Is he here? Hopefully he won't watch it. So basically they have three axioms which are nice, and they are things like if you apply a function to the elements on which the distribution is defined, this in general changes the entropy. And then they demand that if you have two functions and you compose them, that the total change in entropy should be the same as the sum of the individual changes. So they have those kind of axioms. This is also one about what if you take a probabilistic combination of functions. There's three, and I can't remember the third one now, but it's nice. I recommend looking at this one.
And it's up to it.
Sorry?
Up to multiple constant factor.
The result. Yes.
Right.
Yes, it is, yes. The answer that I'm going to focus on is that it depends on your task. So given some task where the input is described by a probability distribution, what is the best that you can do? And often this depends only on the entropy of the distribution. So some examples are coming up. Okay, so this is a very clean one. So suppose you have a probability distribution of messages, say. So this is probability of the most likely message, probability of the second most likely, and so on. It has some peak probability, P max, and it has some width. By this I mean the support size of P, meaning the number of non-zero probability events. That's what this means. So, okay, if someone says, I'm going to send you something from this distribution, you need to build a physical device that stores it in a uniquely retrievable fashion. How many states does the memory, this system, need to have? So you need to have one per possible message, right? And you don't need more. So you need 8 in this case. And then if someone asks you, okay, so how many bits should that memory be made of? Then you take the log to the base 2. Log in this talk is to the base 2. Why did I write 2 bits? Sorry. Yeah, 3 bits. Okay. 3, or you can write on this screen. Okay, this is a tactic to keep you on your toes. Okay, so this is the number of states, and that's the number of this equation, is correct? That's the number of bits. So in general, this is the general expression, and that's the S0, the max entropy. So the memory size is not given by the Shannon entropy, but by the max entropy. This is another one, which is, now let's use the same example, but suppose that you're a very poor casino, and you have a roulette wheel, and it only has 8 entries, so that I can reuse the same graph. But actually the roulette, it has, it's uneven, okay? So this ball, or metal ball, whatever it's called, in the roulette wheel is more likely to land here than here, and so on. But you want to make it uniform. You don't want to have that, right? Because then people will bet on this one. So one sort of poor man's solution to this is to add together different events. So you add together, you could call these three are event 1, and maybe these two are event 2, and this, so 3, it's 2, this would be the other event, and then the final one, okay? And this way you can build, by coarse graining, you can build a more uniform distribution. But you can never go above the limit set by this guy. So this guy, as in you can never get rid of that. By coarse graining, you just add probabilities together. You would want to sort of squeeze things down, but in this game, with what you're allowed to do, you can't do that. So the best you can hope for is a uniform distribution with height p max. Okay? So at most we can hope for a uniform distribution on 1 over p max events, because the height is p max. So at most, so this is a bound now, we can get log of 1 over p max s infinity random bits. It's a bit of a simplified argument, but it's correct. So the min entropy comes out when you're interested in trying to create uniform distributions over bits. So there's often some sort of adversary that you want to make your adversary's probability distribution as uniform as possible. Why does everyone say that the Shannon entropy is the entropy to use? So it has to do with the large n IID limit. So it's common sense Shannon to assume that the random process that you're interested in is independently and identically distributed. So that's what IID means. So the total distribution is the product of the individual distributions, and this n is large. Are you happy with this notation? Do ask me if you're not. Okay. Okay, if you have those kind of states, then you have a neat type of information compression, which is that as n gets large, a large sequence of outcomes, such as a bit string 00111. So you have a distribution over those. They will very likely have about n p00s and n p11s, or something close to that. So effectively, we actually have a probability distribution that's uniform on these sequences, which are called typical sequences. So effectively, it's not exactly true, but effectively, we have a uniform distribution in this limit. So how many of these are there? Call it n-tip. So each has probability given by this, because you have n p0s. And I'm also using the special form of it to calculate that. But this has to obey normalization, this equation, so it's less than or equal to 1, and it's going to tend to 1. You have to be careful with epsilons and so on, but you're going to get the probability of getting a typical sequence is going to dominate as n goes to infinity. And then you get, just from that, mathematically, that n-tip is equal to this, which is equal to 2 to the power of n of the Shannon entropy. So that makes the Shannon entropy special. It's associated with this IID large n limit. It gives you the number of typical sequences. So we have effectively a large uniform distribution for large n, a uniform distribution over 2 to the nh possible states. And if you have a uniform distribution, any entropy gives you the same number, which is log of the number of entries. So any entropy will be log of the number of typical sequences, which is n times h.
We call it s before.
Sorry?
We call Shannon entropy s before, not h.
Sorry, I tried to remove the h's. I've switched. So this is s. Okay. Sometimes it's common to call the classical one h and the quantum one s, and I switch between conventions. Thank you for pointing that out. Is it okay so far? Okay. So away from this IID limit, I try to argue now that S0 and S min, so that's S infinity, are actually the answer to those important questions. How large should the memory be? How many bits can you extract? Uniformly random bits can you extract? And this is from at least I've learned it from this approach by Renato Renner and Stefan Wolf and many others at ETH, where this approach is called the single-shot information theory. The single shot means, the name is from something like, oh, we're not assuming many copies of states. So if someone says, I give you state, they actually mean they give you that state. They're not giving you n copies of that state. So in this limit, there's IID large n, there's just one entropy, but actually, if you go away to the general case, there's two different ones. They can have wildly different numbers. So I'm not going to talk about our research on thermodynamics very much, because I chose to focus on these things, but I want to give you a very simple example of why entropy enters in thermodynamics as a quantifier of how much work you can extract from a system. So suppose you have a heat bath, a system, and a battery. There is a notion of free energy F, which is U minus T, where U is the internal energy, the average energy of the system, T is the temperature of this heat bath here, S is the entropy of rho, or of the system you're interested in. Now normally when you have a battery, you want it to have low entropy. So I'm going to make this extreme simplifying assumption or demand that the free energy of the battery needs to be dominated by its energy, and that I can ignore the entropy contribution to that. Okay, so then I can write, and this is actually involves a second hidden assumption, but I'm going to assume that I can write the free energy as a sum, roughly, of these two things. So then it becomes F1 plus U2, where I'm talking about the free energy of these two systems. So as they interact with the heat bath and nothing else, then this free energy should go down. Why? Well, so this free energy is basically a measure of how far you are from the thermal state. So you can actually formally write it as the relative entropy between the initial state of the system and the corresponding thermal state. So basically, therefore, if you have a thermalizing process, you will want to model it as something that takes you to the thermal state. So you will demand as part of your model, when you're modeling this, that the free energy goes down. So therefore, the change in free energy of 2, which I assume was approximately the change in energy of the battery, so that's what you're trying to get out, you want to get work out, is bounded by the change in free energy of this guy. So you have to, if you want to pump up your battery, you have to take free energy from this guy. Yeah?
We are assuming that the entropy of the battery does not matter also at the end.
Yes, I'm demanding that throughout, which is a very strong limitation. So this is like a really simplifying assumption. In practically any realistic scenario, this guy will get noisy to a significant extent. Yeah?
What is the physical meaning of requiring that approximation?
So the battery, I'm thinking of it as a big classical system, like a weight that's being lifted. Okay, and I don't want it to go like that.
In this case, it might have a big entropy even it has a well-defined microscopic state.
Mm-hmm. Yes, I think this could definitely be, in reality, an issue. But I think that you can find models where you can. There's actually a paper by Skripchik and Short and Pesco, anyone else, where they give you a scheme where they actually keep this entropy under control. So it doesn't blow up. But it's definitely this is a strong assumption, but I'm making it just to make this example simple. I'm not trying to make the most general statement, I'm trying to make a simple example. So I'm going to define this as the work in this case. If there was a significant entropy, you would probably want to define work more like the free energy change in the battery. So you have to subtract the entropy. And you see that then it's given by how much energy can you pump into your battery. It's given by the free energy difference under these assumptions of this guy. So you have to do something to make this worse in a thermodynamical sense. So for example, if you imagine a gas in a container and you expand it, okay, that lowers the free energy of the gas. Because it increases its entropy. Okay, so therefore you see, actually it's not quite true even when I said that it's about the entropy alone, but it's also about the energy change. And that's often a problem in thermodynamics, is that it's not just about probabilities or elements, but the energy matters as well. Okay, so there's a lot of subtleties, which I'm skipping over. And actually we've been thinking a lot about this, and Lydia as well, and several Korean people in here. And we find that if you set up very specific scenarios like this, and you ask more detailed, careful questions, like for example, what is the worst case work? So the sort of bottom tail of your work distribution, what determines how high you can get that number if you're talking about work out, then it's given by S0. So even in thermodynamics, the von Neumann entropy is under attack. Okay, but now I'm going to go back to the information stuff. So just to recap, probably you've all seen this, the Shannon entropy can be written as an average of a fluctuating quantity, which you can call a surprise, log of 1 over pi. The mutual information can similarly be written as an average of this thing. So this thing is called the stochastic mutual information. This is the difference between the log of the conditional probability and the non-conditional. And then there's an important one, the relative entropy, which you will have seen probably, but it's the average. You can write it as the average difference in surprise of two distributions. And you have to choose which distribution you average over, so therefore it's asymmetric between which distribution you choose to average over. So a small, kind of boring technical thing, I shouldn't say boring, but a useful technical thing, is that if you want to prove that these things are non-negative, then it's useful to use this formula called Jensen's inequality, that if you compare the average of a function versus the function of the average, then there's a bound like this. And that also holds in particular for log of x. So I drew that function here. So this would be x on this axis and log of x on this axis. It's useful to draw these things to remember which way the inequality goes. So if you compare now, first of all, the function of the average, so the right-hand side, the average is this guy, that's the function of the average. This guy is the other one, the average of the function. And you see there's a bound, there's an inequality. And you can use that to prove, I think I'll just leave that for reference for those who want to look at it later. You can prove that the relative entropy is non-negative. And the mutual information can be written as the relative entropy between the actual probability distribution and the corresponding product distribution of the marginals. So the relative entropy being greater than or equal to 0 implies that the mutual information is greater than or equal to 0. Is this okay? Am I going too fast? I'm just wary that I need to get onto the quantum part. Yeah, okay. Okay, so another important point is that coarse graining reduces classical entropy. And this is related to John's and these guys axiomatization. You can see that by looking at the alpha entropy, and clumping events together gives you this difference between this would be from the unclumped distribution, and this is from the clumped distribution. And if you think about it, you'll see up to the subtlety, you have to take the limit of alpha goes to 1 for alpha equals 1. You see that this is actually less than or equal to 0. So coarse graining an event gives you a decrease in general in entropy. An important type of coarse graining is taking a marginal distribution. So if you take a marginal distribution, you're clumping things together. So we can write it in this way. Hopefully you understand the notation. And then if we write this thing that we define as the conditional entropy, actually you can define it in another way and show that it's equal to this, but you have seen this probably. This guy then must be non-negative as a consequence. And I'm going through this because many of you will know, this is actually violated in the quantum case. So there's an even more general statement than this, which I think is very interesting. Oh, yeah?
Yeah, what do you mean by coarse graining? Because I would say the opposite, that coarse graining increases entropy.
So I'm clumping events together. So like for example, if I have and now I clump these two events together. So I get a new distribution, which is 1, 0.
Okay.
So there's this thing called the data processing inequality. So quite a general type of data processing scenario can be phrased as applying a stochastic matrix to a probability distribution. So you probably know this, but so that means that I have like P1, P2, P3. Now I have a matrix that goes the wrong way around like that. I just remember that there are it should be that way around. It's not an error. So this thing is called a stochastic matrix. The entries are probabilities, and the columns sum to 1 in order to preserve normalization of this distribution. So if you have a stochastic matrix like this, then you're going to hit. You have some initial distribution. You hit it with it, and then you hit it again. The mutual information is actually going to be worse at the end, which is maybe what you would imagine. So the mutual information between x and z is less than or equal to the mutual information between these two steps. Just a very quick proof sketch is that the mutual information between y and z, x versus y and z as a joint variable, is the same as that. Which is basically because you assume that the stochastic matrix, you assume a stochastic matrix evolution, and that is actually Markovian. So you don't need to care about, it just cares about the latest, the nearest neighbor event in time, in this sense. So, and then you use the fact that this mutual information between of x and y and z is actually greater than or equal to x versus z. And you put these things together and you get the data processing inequality. And you can draw it as x and then something happens, which could be your channel, your optical fiber or something. And this last thing, it could be another optical fiber, or it could be some sort of decoding thing that gives you the thing you're interested in. So one research question here is, how is this related to bias at all axiomatization of the Shannon entropy? Because I think it's the same kind of thing that they're thinking of actually. Because so coarse graining is an example of a stochastic matrix. That's why I say this is more general. Are people following? No, sorry?
Did I miss something? Did you talk about triaxial before?
Oh yes, sorry, that was the one in the beginning,
Oh.
where you asked about the multiplicative constant. Sorry, I went a bit suddenly to that one, didn't I? Yeah. Did you know, yeah? Oh, yeah? Okay. So, part 2, quantum entropy. So, as I mentioned, you have a density matrix rho, a matrix with complex numbers, right? The eigenvalue spectrum of this we're going to call lambda. In the eigenbasis of rho, you can write this as that. Is this notation something that people have seen? There was someone from computer science. Is this, no? No? Yes? Yeah? Okay. Good. So, then don't hesitate to ask if I don't define something. Okay, then you can write the von Neumann entropy in this way. So you see it's the same as the Shannon entropy, but you're using the eigenvalue spectrum. Similarly, you do the same trick with the Renyi entropy, and you define it in terms of the eigenvalues. The simplest interpretation of these things is a measure of our ignorance of the underlying quantum state. And these guys are 0. You can verify if the state is pure. So pure means that one of these is 1, and the rest are 0. And then in the audience we have Carmen Constantine, who's writing up her PhD, or it's called DPhil here, thesis, and it raises an interesting question, which is why should this thing be just one number? Why should the entropy of a quantum state be one number? Because we have many measurements. So why is it not a vector, or a collection of numbers somehow, one for each measurement? So they investigate this object called the contextual entropy. I don't know if she's, yeah, is it correct? Yeah? Okay. And they, for example, they use it as an alternative way of actually representing the quantum state itself. So a collection of all entropies of all measurements. I will remark on that in the connection with generalized probabilistic theories later as well. Okay, so you can understand a lot about this entropy. I think I didn't know that at first until I started reading these papers by Alex and Wilson and others. That the Shannon entropy, this is the Shannon entropy minimized over all measurement basis. In a way, it's obvious once you hear it. So by the Shannon entropy of a basis or a full rank projective measurement, I mean S of rho and some measurement. And you put in the probabilities. This is the probability of outcome I, and this is the probability of outcome I here. So this is just the Shannon entropy. Right? So for example, if rho is plus plus, where plus means this superposition, this linear combination of these two vectors. For the case of this measurement, S is 1. Those of you who are familiar with qubits will probably see that straight away. But for the case of this measurement, the entropy is 0. But actually, this one gives you the von Neumann entropy is the point. So this measurement is the one that gives you the von Neumann entropy. Why is that the case? Why is it the minimal entropy, Shannon entropy, over all measurement bases? So suppose your state is prepared in some basis. So we can write rho like this. And then we measure it in another basis with elements u times j. Okay? Then the probability that if you started in state I, so this means let's assume that we started in one of these states I, and later we find state j, which is one of these. That's given by this expression. This is like the key rule of quantum theory, right? The Born rule. And that you can write that as just the matrix element of the unitary mod squared. This matrix of these guys is what you call doubly stochastic. So that means that not only the columns sum to 1, but also the rows sum to 1. So the columns sum to 1, basically because this is a complete basis that you're measuring in, so it has to be like that. The rows sum to 1, that comes from the specific unitarity. You can write it out as this thing is uji mod squared, and then you sum it over the entries in the row. And then because u dagger u is identity, so dagger means that you take the transpose and the complex conjugate, is given by the diagonal entry of the identity matrix now. This is 1. So okay, that's just it's basically the rows sum to 1 because it's a unitary. So
Sorry, so M
yeah.
you meant.
Sorry?
You wrote M as doubly stochastic when you meant U as being unitary, right?
Yeah,
M as doubly stochastic when you mean U is unitary. Is that right? There's no M here.
did I say something? Sorry, this is M.
Where is that?
So I'm pulling the transfer, this matrix of these entries.
Oh, I'm sorry. I'm sorry.
No, thank you for asking.
Yes,
It's great that you.
Yes.
So yeah. So you have.
Yes, sorry.
Yeah. Okay. So you have some probability. These lambda i's are the probabilities of different i's, and then they evolve to the probabilities of j under this matrix mij. And mij is doubly stochastic. So to visualize that, if you have, with these Stengel magnets, the basis choice is the angle at which you measure. So if you prepare something, so your first measurement is this, that would be your I basis, associated with the I basis. Then this guy, if the rotating U is non-trivial, this is at an angle. But you don't, if you want to keep the entropy low, you should not do that. You should keep it back in the original position. So turning this guy around is like a noise tap. It's like the more you turn it, the more noise you get, but then actually after a while the noise starts to go down as you end up measuring basically a permuted version of this basis. So basically you should stay in the diagonal basis if you want to keep the noise down. And now I'm just asserting, but I think I'll probably prove it in part 2, that doubly stochastic matrices cannot decrease entropy. We'll see that why that is, but basically they take the distribution towards a uniform distribution. So if you sap a probability distribution with a doubly stochastic matrix, it's not going to get less random. Yeah. Is this okay? Okay, so now why can coarse graining increase quantum entropy? So if you have this state, 0, 0 plus 1, 1, the joint entropy is 0 as it is pure, but the local entropy, as many will know, is 1. The local measurements are random. And the key thing here is that different measurements minimize the Shannon entropy in the AB versus A case. So if you wanted to do a measurement to check which pure state this is, you have to do a Bell basis measurement, a very global measurement. So to make that a little bit more precise, consider measurements of this product form. So let us call those prod. These yield classical joint probability distributions when you measure, which we can call PAB. And because these are classical joint probability distributions, from what we had before, S of A is less than or equal to S of AB for those distributions. And we can conclude with a little bit of thought that S of rho A is actually upper bounded by the best case Shannon entropy for all of those prod measurements. So, but crucially, not all measurements are of this type of prod. In particular, the Bell measurement is the extreme counterexample where you use basis elements like this. And Sheila has a t-shirt, but not today with this. So that means that we can have S of rho A being greater than S of rho AB. Just that this is not a minimization over all measurements. It's that simple. And if we have that, then the conditional entropy, normally defined like this, is negative. So you can have negative conditional entropy, and basically it comes down to the fact that there can be measurements that are not of this product type that could be minimizing the Shannon entropy. Then I just briefly, I was thinking, oh, this is basically what people are talking about when they talk about Discord. Is there anyone in here who has done papers on Discord? Oh, okay. So I wanted to ask something about Discord. So yeah, I noticed this. So if you have a classically correlated state, then you normally define it like that. Actually, it should. Yeah, I could have had a J there to make it more general. Then again, we can have so for these types of states, then actually the entropy is the same as the one where you minimize over product states. So therefore, I think that we can use this difference of a state. So the state may not be classically correlated with this quantity as a measure of non-classical correlations. And I wanted to show that that's what the Discord people are doing. But it is very similar. It's very similar to this thing. So this is in Kavan-Modi's review and others, which is called the symmetric quantum discord. That you have the mutual information of this corresponding to the product measurement, maximized over all product measurements, and you compare it to the actual mutual information, and this they call the symmetric quantum discord. And the sort of states that have non-zero values for that is this one. So this is a typical non-classically correlated state. It's actually not entangled, but it's not of this form because of this plus here. So I don't actually work on Discord. I just felt like it was so similar that I had to mention it. So okay, what about that data processing inequality in quantum theory? Okay, this someone has this up in the physics department. It's not very positive. Some of the highlights, I think this one is good. The light at the end of the tunnel is the headlamp of an oncoming train. Friends come and go, but enemies accumulate. But, okay, so I want to add something to this. The data processing can only degrade data. Okay, so DPI, data processing inequality, also holds in quantum theory. You can write it as the mutual information of two things is better, higher, than after having done something to B. And that can actually equivalently be written as in terms of the conditional entropy. And what you can do to B is the most general trace-preserving transformation. So this has a technical name, CP-TP transform. And there is a very simple proof, although it's cheating because I'm using a property which has not such a nice proof. But I don't think I want to go there. I'm going to assume this one. So I'm going to assume something called strong subadditivity, okay? And it's this property that the conditional entropy, when you trace out C, obeys this. it seems very nice that conditional entropy should have this property. And I'm going to use the fact that these transforms can be implemented by bringing in an ancilla, applying a unitary on the ancilla. I'm going to call the ancilla C, so it is the same C as here, and followed by tracing out C. So in terms of state, we have rho AB tensor 0 on C, and it evolves under this unitary on BC, and then I trace out C and I get some new state on rho AB. So in terms of entropies, I have some conditional entropy here. I get a new one. I wasn't sure what to put as an index here, but this is now after the unitary. But that one is actually the same, because it's just a unitary on BC. If you write it out, you will see that it's good. So yeah, it is. Then you trace out C, and that gives you HAB prime now. Using, so this is where we use this strong subadditivity that we've traced out C, so we get a bound to the previous one, and that one was equal to this one. So maybe, I don't know if you probably have to write this out for yourselves to follow it, but at least you can see that if you assume strong subadditivity, the proof is not difficult. Okay, this has an annoying consequence of bounding the communication rate in the sense of mutual information between two parties. Suppose Alice has a classical message I with a distribution pi, and she prepares a quantum state conditional on that message. So she generates a joint state, pi. This is her classical part, and this is the corresponding state that she prepared for Bob. She sends her part to Bob, and actually this is for an ideal channel, but it could be noise in here now. If there's no noise, then she would have this mutual information after having sent it, which is just the mutual information of this state, which you can rewrite in this way. Bob now does a measurement with Paul's generalized measurements, possibly. And he takes rho b to be concrete. Let's say that he takes it to a new state, which is a mixture like this, like a classical state with the probabilities of the different outcomes. DPI applies to those sort of maps. So now the classical mutual information that has been established, because after this, it's a classically correlated state. So we can call the mutual information classical. The one that we have established respects IAB prime is less than or equal to the original one, and that is less than or equal to log of the dimension of A, because this entropy is less than or equal to log of the dimension of A. So this is Holevo's bound, and it's annoying because it seems to say that we cannot cram more classical information into a qubit than into a classical bit, because a classical bit can also be used, or a classical d-dimensional system can also be used for log of dA information, mutual information to be transferred. But then there are some tricks like super dense coding that allow you to actually use a pre-shared entangled state to do twice as well. So it's not fully bad. Okay, so the reason I went through this DPI is that it's going to come up in these papers. So first one is called Entropy and Information Causality in General Probabilistic Theories, and we have one of the authors here, Alex Wills. Then there is Entropy in General Physical Theories. I think these were even in the same NJP, what do you call it, the same release. Then we also, myself and Daniel Larscher and Renato Renner, have done a follow-up which had the same results of that, where independently discovered by Tony Short and Sabri Al-Safi in Cambridge. And we also concluded that you could go further and say that the data processing inequality alone implies zero-sums bound. But there are some important conceptual caveats. Okay, so the general reason to be interested in this that I already mentioned is that if information theory is a meta theory, in the sense that it should be independent of the underlying physics, then it should hold in any probabilistic theory. Maybe you want to be a bit kinder and say any reasonable probabilistic theory or something like that. So let's start with a very simple case. Let's say you have a data table. What is the entropy of a data table? And this perspective on presenting these theories is from Jonathan Barrett and Lucian Hardy and Piero Mana. Is this his name? Do you remember? Mana is his last name. Who is actually, I believe, in Oxford now doing atmospheric physics. So you have a data table, two measurements, M1 or M2. Okay? Each one gives you +1 or -1. And I didn't write that to annoy Dan, who was saying that we shouldn't use plus or -1 earlier today. These guys have some relative frequencies, for example 0.5 and 1, 0. So this could, in the quantum case, this could be Pauli X and Pauli Z, if you like, or something like that. So in this case, we have two equally elementary measurements. So it's really like the quantum case. So what is the entropy of this data table? Well, we have to choose how to define it. So one option is to define it as the minimal Shannon entropy over these measurements. And this is how it's done in these papers. There's actually two routes that were pursued, but I'll just focus on one for simplicity. And that is called the measurement entropy. So the measurement entropy of a table, and actually we're going to start calling the tables states. The measurement entropy of a state is the Shannon entropy minimized over measurements. And you have to be careful that they should be, in some sense, equally fine-grained.
Question?
Yeah.
So presumably these measurements are supposed to be tomographically complete.
These
measurements are supposed to be tomographically complete in the operational theory that we're talking about. So to be able to define this notion of measurement entropy, isn't it a prerequisite to be able to say that a certain set of measurements is tomographically complete in this? Or is that like an assumption that the data table consists of a set of tomographically complete measurements?
So at the moment, I'm just saying, I'm not assuming the full structure of these theories. I'm just saying I have a data table, and I want to assign. Sorry.
That there is a fiducian set of measurements.
No, this is correct that if you wanted to represent a quantum state in this way, in such a way that the state is one-to-one with the table, then you need, for example, Pauli X, Pauli Y, Pauli Z. And that would be a tomographically complete set. Although actually you're not even in the minimizing, you have to minimize over all equally fine-grained measurements. So not just over the tomographically. So the measurement entropy is a very simple way of defining entropy of a data table. So why do people talk about a data table as a state of a system? So different tables for the same measurement outcomes. So that means that we're going to keep our measurement apparatus, and we're going to repeat our different versions of our experiments and build up statistics for each version, for each preparation. Different tables would give different preparations would give different tables. Okay, so these are just different real vectors. So each data table is associated with one way of preparing the system. The set of all allowed data tables is the set of states. The set of states is thus a set of real vectors. So it's actually very simple. Normally you allow if you allow one preparation, you allow probabilistic combinations of such preparations. So you have a convex set of states. To get a data entropy, to get a data entry from these guys, how would you do that? If I start giving you a vector, how are you going to get the data entries out? If you were doing computer code or something, you could write a vector. For example, we wanted to get this one out. So you're given the vector 0.5, 0.510. If you want to get this one out, you can dot that vector with 1, 0, 0, 0. That's an effect, which in the language that Paul has used. So there's a set of effect vectors, and these are actually implicitly already there when we decide on the data table structure. So they actually logically precede the state in that sense. So the state assigns, these numbers are assigning probabilities to effects. The set of effect vectors are these real vectors, together with a set of state vectors and the set of transformation matrices. So these are real matrices. That's how you transform your states, with real matrices. That gives you a theory, by definition. So it's actually very simple now. It's real vectors for states, real vectors for effects, real matrices as transformations. And you're actually used to doing this in quantum theory, most of those who do quantum theory, because you use the block sphere, for example, which is a real vector representation of a state. So in the block sphere, remember you have rho is where these are G is identity X, Y, Z, right? So the block vector is, you ignore this case, and you write the coefficients of these guys up to a constant. So you can, but you could write the state like this in general, and then these guys are real numbers. So a quantum state can be represented as a vector, just rho. So your quantum state is a real vector. And similarly, you can expand your operators, measurements and so on in this basis, and you get the same kind of vectors. Then taking the Hilbert-Schmidt norm becomes taking the inner product. So if I have trace rho something, this is the same as rho dot the corresponding vector for that one. Do you see? So you can represent quantum theory with real vectors. And I should have, I realized that I should have added Paul Bush's name to this list, because they have done something very similar. So an interesting example that I think Howard will mention is what's called a square bit, okay? Or it's also called a G-bit in Jonathan Barrett's paper. So we can suppose that we can prepare these things. So we have one measurement and another measurement. These could actually be two coins that I flip, but for some reason you're only allowed to measure one. You're not allowed to do a joint measurement of the coins. So this would be for some preparation that I or a machine makes. They're always heads. Okay, when you check coin 1, it's always heads. When you check coin 2, it's always heads. But you're only allowed to measure 1. That's a bit subtle. So there's no effect for both of them. If you have these 4 states, and now you can see, oh, these are probabilities. So actually, I don't have to. I can draw it in 2 dimensions. You might worry about drawing it in 4 dimensions, but because these guys sum to 1, actually I can only take. I can get away with just plotting this entry and this entry to specify the state. Then I get these points. So, for example, this one, x is 1 and y is 0, gives me this point. Okay? X is 1, y is 1, gives me this point, and so on. And then if I take probabilistic combinations of these guys, you know, if you take a convex combination of 2 vectors, you end up on the line between the 2 vectors. So a convex combination of this one and this one is on this line. A convex combination of this one and this one is on this line. So if you form the set of all convex combinations, the convex hull, it's this whole square. Therefore it's called a square bit. Okay. Now this is not going to respect the uncertainty relations if you take these to be, say, Pauli x and Pauli y, these 2 measurements. Because you have, for example, in this state, Pauli x would be +1 and Pauli z would be +1, which that doesn't exist in quantum theory because of the uncertainty relation. But you're not allowed to measure both at the same time because there's no data entry for that measurement. So this is, people call this, and I think this is entirely consistent with your definitions, they call it a case of complementarity without uncertainty.
That's the old Roche-Beckens toy model?
Sorry?
That's the old Roche-Beckens toy model?
Roche-Beckens toy model is actually slightly different. It's a turn square. So it's
12%.
yeah. So there you have. It's like the stabilizer states. So in his toy model, he can prepare these ones. Yeah. So he has the uncertainty principle, which is what he wants to create, because he says you can only know 1 bit. Yeah. So he wouldn't. He would have had 1, 0, half, half. And now this is from these papers by Alex and others, that there seems to be a violation of the data processing inequality in this type of theory. So consider 2 random single bits, A and B, and their values are also copied into the data table, which we call C, so that means the G bit. So the outcome of the first measurement would be whatever the outcome would be for A, and the outcome of the second measurement would be whatever it's for B. Now, let's see. So I hope I have done this correctly because I did it from memory now. Well, not from memory. I tried to recreate the argument rather than write it down straight from the paper. So first of all, very importantly, we define the conditional entropy as SAB minus S of B. That's a very natural, sort of naive thing to do, but I think we all sort of agree that have worked on those papers that this is actually a bit arbitrary. And this is probably implicitly doing something to the effect of putting a restriction on the theory in conjunction with the data processing inequality. I will probably just confuse you the more I talk about that point, because I'm not sure yet myself what the answer is. But there's something there that this definition is very arbitrary. So do remember that there's this definition. Now, then it follows that SA conditional BC is given by this. And if we evaluate that with this measurement entropy definition, we find that it is Yeah, this is right there. That is 2 minus 1. So 2 is from this term. You have A, B, C jointly, and A and B give you 2 bits of randomness, basically. You could try and do a joint measurement on, because one of these is copied, they're both copied into the other system, but it's not going to help you to do a full measurement. You can't just look at the G bit. To do a full measurement, you have to do both bits. Then SBC is 1. So B is C is the G bit, which includes B in it. So there's only one random bit. I wonder if this may be difficult for you to see, but if you just believe me, these are 2 minus 1, which is equal to 1. That should be uncontroversial. Then S of A given C is actually 0, because because S of AC minus S of C are actually equal to each other, because A is copied into C. You probably don't see fully where this line comes from, but just see the numbers, okay? That it gives you 1 and 0. So therefore this guy is bigger than this guy. And this violates strong subadditivity. And you can derive strong subadditivity from DPI, so it also violates DPI. So it seems like there's a violation of the data processing inequality. And that's also why we did these things of saying, what if you demand that the data processing inequality holds, and then you can get the zeros into bound. But there's something that is not fully understood, which is this definition and the role of this definition in this argument. So that's a research question: is why does this definition, work together with DPI? So it doesn't violate DPI using that definition in the quantum case, but not in the general case.
In the classical case as well, right?
Yeah, in the classical, yes. But somehow I think the classical case, it's probably not so strange that they work together. Yeah. Okay, so there are many possible ways of defining entropy. It depends on what property you're interested in. The quantum von Neumann entropy is the Shannon entropy minimized over measurements. The conditional entropy can be negative in quantum theory, and it follows from the fact that different measurements are used to evaluate SAB and SB, and you optimize. And you can similarly define entropies of data tables, or even generalized probabilistic theories. And these data tables do not have to represent quantum states. Some odd things can happen there, however, so it's very interesting to understand what's really going on there. A very quick preview. So when two probability distributions are related by a double stochastic matrix, which I have defined now, one says that one distribution, the one that gets hit by the matrix, majorizes the other. It is less random. You can use that as an alternative definition of majorization. And this actually implies that the entropy of the latter is at least as large as the former, but it is not the other way around. So majorization is a tighter condition than entropy difference. Now, and we're going to discuss these sort of things in the next one. Okay, so thank you.
Thanks, Oscar. Question or two? I'm quite tired.
Thank you for sticking.
Could you go back to the first research question? I didn't.
The first, the one about bias, but
Whatever it was.
I think that was the first. This one?
No.
No?
I guess one before that.
Was it?
There was one.
I don't remember.
I think it was something to do with conditional entropy in the classical case, and I couldn't understand what the question was.
I think that was the one that was the, yes, sorry.
Oh.
This, I think, okay, so that's probably because I didn't really explain it much. So they have a paper, Bias and Fritz and Leinster, that derives the Shannon entropy from some axioms. And these axioms concern what happens when you hit the sample space with functions. And I think that these functions fall into the domain of applicability of the data processing inequality. So it includes things like coarse graining, which is included here. So I think that there should be a relation between their derivation of the Shannon entropy from their axioms, and there should be some, for example, a derivation of that style of the mutual information.
I think what I was reminded of was the fact that in the classical case there's a proof of the uniqueness of entropy, the classical of Shannon's entropy, using basic rules about what you consider to be information, what is information.
Yep.
And the logarithm turns out to be quite a major role in that. And so I was sort of curious about this, that they have another derivation.
They have another one. I mean, it ties in with the other. They use some results from older ones, from older derivations. But it's also important to remember that there's some of the assumptions that you use to derive the Shannon entropy are quite specific.
Yeah.
And that's sort of what Renier said, is that if you weaken these assumptions a bit, you get this wider family of Renier entropies.
I understand. Thanks.
Okay, we're pretty much out of time, so let's thank Oscar and all the other speakers today for a great first day. So time to have a nice evening.